Welcome. Today I'm going to talk about information set Monte Carlo search trees in the game Coconuts. I love playing card games, so I found the chapter about adversarial search very interesting. For my project, therefore, I decided to create a card game that will have human players play against computer players. I will first talk about my objectives and a brief overview of the game Coconuts and why it is interesting for AI. Then I will discuss the approach I used and the results of my project. I wanted to explore AI techniques in games where some information about the current state of the game is hidden from the players. For example, in card games, players cannot see the cards opponents have in their hands. We say these games have imperfect information because the player does not have all information about the current state of the game. The hidden information creates a challenge for the AI player because it is more difficult for the AI player to predict how opponents will react to certain moves. In games of imperfect information, the AI player must use probabilities to guess at the cards the opponents are holding, unlike games of perfect information where the AI player knows exactly what moves the opponent can potentially make in response to the AI player's moves. My goal was to implement an AI player for the game of Coconuts. My goal for the AI player was to make the AI player challenging enough for the game to be fun, but I wanted the user to be able to win. Additionally, the AI player cannot spend a lot of time looking for the optimal move. Probably a few seconds at most, because human players will think the game is slow or get bored waiting for the AI player to play, if it takes too long for the AI player to select a move. Finally, the AI technique used must select moves that the human player will perceive as appropriate. The human player may perceive the game as buggy or flawed if the AI player play moves that seem random or strange for the circumstances, even if the AI player ends up winning the game. I decided to use the card game Coconuts, which has many variations and goes by other names, including Karma and Palace. The rules are simple. Each player is dealt 9 cards, 3 cards face down on the table, 3 cards face up on the table, and 3 cards to hold in the player's hand. On each player's turn, the player tries to discard a card that is equal to or higher than the top card of the discard pile. If the player cannot play, the player has to pick up the discard pile and add the cards from the discard pile to the cards in the player's hand. The goal is to be the first player to discard all of your cards. What makes Coconuts tricky is that the face-up cards are only played after all cards have been played from the player's hand, and the face-down cards are played only after playing all face-up cards. And you can't look at the face-down cards before playing the card. Coconuts is an interesting game for AI because the Coconut is a game of imperfect information and involves some randomness. The game begins with a shuffled deck, which introduces randomness into the game. The AI player does not know what order the cards will be drawn in, so the AI player cannot know exactly what the outcome of a move will be. This makes it more difficult for the AI player to determine a series of moves that will move the AI player closer to winning. Some of the information about the current state of the game is hidden from the AI player, namely the other player's hands and the cards that are face down on the table. The hidden information makes it difficult for the AI player to predict the opponent's responses because the AI player does not know what cards the other players are holding and in what order the cards will be drawn from the stockpile. Finally, at any given point in time, it is difficult for a player to gauge how close he or she is to winning and how much closer to winning an individual move will put the player. The player may appear to be winning because he or she has the fewest cards, but the player may still lose if the player's face-down cards have low values or the player has to pick up a lot of cards from the pot. This makes AI techniques that rely on heuristics difficult to apply. Therefore, the AI approach needs to be able to deal with stochastic games with imperfect information and not depend too much on heuristics. Given the characteristics of Coconuts, I selected information set Monte Carlo tree search as the AI for my card game. ISMCTS is a modification of the Monte Carlo tree search algorithm. Monte Carlo tree search combines Monte Carlo simulations with searching game trees. In a Monte Carlo tree search, the current state of the game is taken and used as a root node of a game tree. The game tree is gradually grown using random simulation, and the results of all the simulations are averaged to select the best move. Each iteration of the algorithm involves 4 steps. First, a node is selected to expand. Then that node is expanded by adding an untried move. Then from that expanded node, the game is simulated to a terminal state, meaning one of the players has won, and that is done using random moves. And then the results of that simulation are propagated back up the tree. The idea is that the statistics propagated up the tree will help guide future iterations of the algorithm to better moves. The problem with applying this to games of imperfect information is that we do not know the current state of the game. In the context of games of imperfect information, determination is used to make the current state of the game a game with perfect information. In determination, the unknown or hidden information is distributed. For example, in card games, the unknown cards are distributed to the players in other stock or discard piles randomly. The rest of the game can be simulated based on these fully observable game state. Since there are often a lot of ways to distribute the unknown cards, a sample of possible states are used. For example, at the beginning of Coconuts, 37 cards are hidden and there are 37 factorial ways to distribute them. There's no way the AI player can look at all possibilities, so some random sample must be used. In Monte Carlo tree search, each of the determination is used as the root of a game tree. Monte Carlo tree search is then used to find the best move in each of the game trees from the sample determinations. The results of all the game trees are averaged at the end to determine the best move. One of the problems with Monte Carlo tree search with games of imperfect information is that the different game trees will result in different moves. But from the player's point of view, all the determinations are indistinguishable. It does not make sense for different moves to be chosen when the player cannot tell the difference between the determinations. Another problem is that the different game trees will search the same moves and states because there are often multiple ways to get to the same game state. To address these problems, ISM-CTS uses information sets instead of determination. An information set at a specific point in the game is the set of all possible ways to distribute the hidden cards from the point of view of the player whose turn it is. All states in the information set are indistinguishable to that player. Therefore, the ISM-CTS grows a single tree using the current information set as the root of a game tree. Instead of creating different trees for different determination, ISM-CS searches the same game tree multiple times using different states from the information set at the starting point. After each simulation, the results are propagated back up the tree. The algorithm uses the same 4 steps as Monte Carlo tree search, except an additional first step is introduced. Thus, the following 5 steps are repeated each iteration. The unknown cards are randomized and distributed. This random determination is used as the root of the game tree. Next, select a node to expand. The tree is descended until a node with the untried move is found. The upper confidence bound policy is used to select which nodes to expand. UCB chooses the node with the highest expected value. How UCB balances exploration of new nodes with exploiting nodes already visited can be adjusted. Next, we expand the node selected by UCB by adding a child for the untried move. The game is then simulated to a terminal state using random moves. The results of that simulation are then propagated back up the tree. Here, those values would be the number of times a node is visited and whether the player won the game. After hundreds or thousands of iterations, the move selected is the move that was visited the most in the simulation. More iterations will generally improve the quality because more possible game states will have been simulated. The strength of ISM-CTS are that it can perform well even without any domain knowledge to guide the search. And ISM-CTS can be stopped at any point, so it can use up whatever time is available for searching and then determine a move based on the iteration it was able to complete. I evaluated the ISM-CTS implementation by having a player using ISM-CTS play against 3 players playing a strategy of always playing the lowest possible move. I used playing the lowest possible move as the strategy because that is the strategy I favor when I play, and it intuitively makes sense to save your higher cards for when you need them later. I tried 1,500, 2,500, and 3,500 iterations and played 50 games at each iteration level. The ISM-CTS player performed about average at 1,500 and 2,500 iterations because they won about 25% of the games, which seems average given the games had 4 players. At 3,500 iterations, the ISM-CTS won 34% of the games, which means the ISM-CTS algorithm outperformed the non-AI players. For future work, I would like to try and introduce knowledge to help guide the algorithm. The AI player takes too long to select a move, on average 44.8 seconds at 3,500 iterations, which is too long for a human player to wait for the computer player to play. introducing knowledge into the game about what cards other players are likely to have based on previous plays or what cards are best to play in certain circumstances may help the AI player make a decision in less time. I will now do a demonstration of my program. The game and the ISMCTS implementation are written in Python. That code can be run without the user interface, which is how I ran the program for evaluation. Human players cannot play in that version. The user interface is implemented using Jathan, which is a distribution of Python that runs on the Java virtual machine. I use Jathan for the interface because I am much more familiar with developing user interfaces with Java than Python. In Jathan, you can basically call any Java library you want using the Python syntax. So let's start the program. The first step after all the cards are dealt is each player gets a chance to swap cards between the cards in his or her hand and the cards face up on the table. The human player does this through the dialog box. In this implementation, the computer players do not swap any of their cards, but that is something that I would like to add as future work. In this project, I wanted a baseline of how well ISMCTS performed, and if I implemented some heuristic or other AI technique for this step, I wouldn't know how well the ISMCTS did on its own, and I wouldn't know how the added AI technique or heuristic in the step impacted the results of the ISMCTS implementation. So I will choose my 3 cards here, and it's probably best to have the cards I'm going to play later be higher, so I'm going to try and choose lower cards to keep in my hand. The human player always starts, and you can tell it is the human player's turn because the human player's label has a red background. The labels will change to indicate whose turn it is throughout the game. The pot is currently empty, so I can play any card I want, but I tend to try and play the lowest card possible to save my higher counting cards for when I need them later. Once I play a card, a new card is drawn from the stockpile and added to my hand because the player must have at least 3 cards in his or her hand as long as there are cards in the stockpile. So the cards here are sorted from highest to lowest, so I'll play my lowest card. After I play, each of the computer players will use the ISMCTS algorithm to determine which move to make. For this demonstration, each computer player is performing 250 iterations, which ensures the computer players will make a decision in a fairly short amount of time for this demonstration. After each of the computer players play, the interface is updated. The ISMCTS algorithm is run on a background thread called a swing worker. The swing worker thread executes long-running tasks like the ISMCTS algorithm and periodically makes updates to the interface. This leaves the event thread free to respond to user input. For example, if I try to play while one of the computer players is making a decision, the event thread is still able to put up a dialog warning, "Me, that is not my turn." It will also only let me play legal moves, so here I tried to play a card that was not equal to or higher than the current card on the top of the discard, and it is telling me that that is not legal. And so if I try to play while that player is thinking, I get a warning that it is not my turn. And that is possible because the swing worker is doing the work in the background while the event thread is still listening for user input. And now this play continues for a while, and we will fast forward a little bit towards the end of the game. As you can see, it is now much later in the game, and we will resume play. So now each player gets to do their select a move. And if I could play, but say I couldn't, I would have to pick up the discard pile, which I would do by double clicking on it. And now all those cards become part of my held hand that I will have to play before I get to play any of these face up cards or face down cards. And as you just saw, the top player had to play their face down card, which are played without looking at them before you get to play them, which is what makes the game interesting. And that card was not high enough, and he had to pick up the rest of the pile. And the play continues like this. The game can continue for quite a while with people having to continually pick up the pile, so I will not play the game all the way to conclusion. If I wanted to start a new game at this point, I could select New Game from the File menu, and it would ask me to confirm that I really want to quit this game since I cannot resume the game once quit, and I will say yes. And now a new game has started. And that is my demonstration. Thank you for watching.